Hi students, welcome to Madras Math Kernel. So today you are going to see about the theory, the concept, theory part and example explanations pertaining to exercise 1.3. This comes under your real numbers. So first, theorem 1.3. What your theorem 1.3 says? Let P be a prime number. If P divides A square, then P divides A, where A is a positive integer. So coming to the proof. So as per your theorem, whenever you say a particular prime number divides A square, then that same prime number should also divide A, where A and A square are nothing but some positive integers, right? So coming to the proof, let the prime factorization of A be. For example, you are considering A as some composite number like 6, 4, some 10, something you are considering. So that number can be written as the product of prime factors like P1, P2, etc. up to Pn. I am taking P1, P2, etc. Pn as the prime numbers. On multiplication of these prime numbers, I am getting A. This is what I am assuming here. And I am assuming they should not be necessarily distinct prime numbers. There may be some repeated prime numbers also. So what will happen on squaring A? So squaring on both sides, it will get you squaring on both sides will give you A square is equal to P1, P2, etc. Pn. This is for A, and for another one more A, I am writing again P1, P2, etc. Pn, right? Therefore, it is given in the theorem P divides A square. So when you say P can divide A square, already we have seen the prime factors of A square. They are nothing but P1, P2, etc. Pn, and again P1, P2 is repeating here. So whenever you say P divides A square, then this P should fall with one of these prime factors, right? Therefore, P should be one of P1, P2, etc. Pn. Also, since A is equal to P1, P2, etc. Pn, we already know A is nothing but A can be written as P1, P2, etc. up to Pn. So here we have confirmed P is falling with one of these prime numbers. P is falling with one of these prime numbers P1, P2, etc. Pn. And also we know A is equal to P1 into P2 into etc. up to Pn. And since P is one of these, we can say P divides A, right? Is it clear? This is the proof for your theorem 1.3. And coming to theorem 1.4, root 2 is irrational. This is your theorem 1.4. So we are going to prove this theorem with the help of the technique called proof by contradiction. That is, what you are going to do to prove this root 2 is irrational, you are going to assume some wrong statement, and at the end you are going to conclude our statement is wrong, what you have assumed is wrong, and the reverse is the right. That's what you are going to conclude. So first I am assuming root 2 is rational, because you are supposed to prove root 2 is irrational. So I am assuming reverse, root 2 is rational. And then what I am doing, root 2 is equal to, since I have assumed root 2 as a rational number can be written in the form of a fractions. So fractions is nothing but P by Q form, where P and Q are some integers. Here I have taken R and S. R and S are some integers. I am assuming some common factor or common numbers is between R and S. So after cancelling that common number between R and S, I am writing new integers A and B. Root 2 is equal to A and B. How I am getting this? After cancelling the common factor between R and S, I am getting A and B, where A and B are the co-prime. Now I cancelled all the common factors, so that now A and B, they don't have any common factors other than 1. So they are called as co-primes. A and B both are prime numbers and they don't have any common factors other than 1. So, you are calling those two integers as co-prime. Then now what do? You take b to the other side. B root 2 is equal to a. So, now squaring on both sides, b on squaring will give you b square, root 2 is 2 is equal to a on squaring will give you a square, right. Therefore, you bring 2 to the denominator of your a square. So, b square is equal to a square by 2. So, what you can infer from this equation, a square is divided by 2, which says 2 divides a square, which implies, as per the previous theorem, if p divides a square, then p also divides a. That is what your theorem says. So, here since 2 divides a square, 2 should also divide a, right. This is first thing you have arrived. And secondly, what I am doing, since 2 divides a, so what I can write, a is equal to 2 times a, because I said 2 divides a. So, I am assuming this as a constant. A by 2 should be a constant c, it is another constant, another integer. So, since a by 2 is equal to c, you can rewrite a is equal to 2c. Perform the same procedure, squaring on both sides. I am getting a square is equal to 4c square. Now, what do? You substitute the value of a square from this previous equation. What is a square here? It is 2b square. You substitute it here. Instead of a square, you write 2b square is equal to 4c square, and you cancel out the common numbers between these two terms. Therefore, b square is equal to 2c square, and again c square is equal to b square by 2. You bring the 2 to the denominator, and what you can infer from this, your b square is getting divided by 2, or your 2 divides b square, therefore 2 should also divide b. Already what you have assumed, a and b are co-prime, they do not have any common factors other than 1. Now you are arriving with the conclusion that 2 divides a and 2 divides b. So, what you are saying now, a and b have a common factor of 2. Therefore, this contradicts our assumption that a and b, they do not have any common factor other than 1. Therefore, what you have assumed is wrong. Therefore, root 2 is not irrational, but rather it is root 2 is not rational, but it is irrational, right. Is it clear? Coming to example 9, prove that root 3 is irrational. You are going to follow the same procedure what you did in the proof of root 2 is irrational, except the first step. There you have assumed root 2 is equal to r by s. Here you are not going to assume that step. You are directly assuming root 3 is equal to a by b, where a and b are co-primes. What it means? They do not have any common factor other than 1. Right? Squaring on both sides, again the same procedure, squaring on both sides, you will get 3b square is equal to a square. So, from this you got the idea that 3 divides a square, and therefore, it should divide a also. So, since it is dividing a by 3, I am assuming it as c some constant, where c should belong to some integers, right. Therefore, a is equal to 3c, a equal to 3c, squaring on both sides will get you a square is equal to 3 square is 9 c square, and then what do? You substitute your a square from the previous step. You assume this as 1. So, b square is equal to a square by 3. So, what is a square? 3b square. So, I am replacing my a square with 3b square. So, 3b square is equal to 9c square. After cancelling the common factor 3, b square is equal to 3c square. So, from this what I am inferring, c square is equal to b square by 3, which means 3 divides b square, and so 3 should divide b also. So, now what I am getting, the common factor between a and b is 3, which contradicts our assumption that a and b, they do not have any common factor. Therefore, what you have assumed is wrong. Therefore, root 3 is not a rational number, rather it is irrational number is proved, right. Coming to example 10, show that 5 minus root 3 is irrational. So this proof is very simple when compared with the previous problem. So but procedure is quite same. So let us assume 5 minus root 3 is rational. Again I am assuming 5 minus root 3 is rational. So rational number means you can write in the form of a by b. So again they are co-prime, a by b are a and b are co-prime. So 5, what do? You bring this root 3 to the right hand side, a by b to the other side. That is, I am segregating all the integers to the one side and all the root numbers to the other side, right. So after bringing all the integers to the one side, I am taking the LCM for these two numbers. So it is denominator b, in the numerator I am getting 5b minus a. So a is a prime number, b is a prime number, 5 is also some constant. Therefore all the three are integers. Therefore after performing the subtraction and division, I will sure get a integer or a rational number only, right. So the entire term is rational. So rational number should be equal to root 3 means what it says, root 3 is also rational, but actually root 3 is irrational. So the fact is root 3 is irrational, but here you are getting it as rational. It contradicts the fact that root 3 is irrational. So what you have assumed is wrong. Therefore 5 minus root 3 should be irrational is concluded, right. And then coming to example 11, show that 3 root 2 is irrational. Again same procedure, I am assuming 3 root 2 is rational first, and then I am equating that to a by b. So after equating, I am segregating root 2 I am retaining root 2 one side and taking all the integers to the other side. So root 2 is equal to 3 will come to the denominator, root 2 is equal to a by 3b. So after performing the division operation here, sure you will get a rational number here, right. In an equation, one side rational and one side, if one side is rational, very sure the other side also should be rational. So if you say this is rational and root 2 is also rational as per this equation, but it contradicts the fact that root 2 is irrational. This is the fact actually, right. Therefore because of this contradiction, we come to the conclusion that what we have assumed is wrong, and therefore 3 root 2 should be a irrational number, right. So that's all the concept and example problems related to your exercise 1.3. Thank you students.